Hello students, today we have to see the next point, vibrations of ear column in a pipe closed at one end. Consider a long cylindrical tube or a pipe closed at one end, just like this. This is a long cylindrical pipe closed at one end. It consists of an ear column with a rigid boundary at one end. This tube consists of such an ear column. This is the ear column with a rigid boundary at one end. At end, there is a rigid boundary. At this other end, there is a free boundary. When a vibrating tuning fork is held near open end of the closed pipe, sound waves are sent by the fork inside the tube. Here, if such a vibrating tuning fork is held near the open end, then sound waves are produced, and these sound waves travel along this ear column as like this. Longitudinal waves traveling along a pipe of finite length are reflected at the ends, as transverse waves are reflected at the fixed ends of string. Here, these sound waves are the longitudinal waves. Sound waves which are traveling along this ear column are the longitudinal waves, and reflection of these longitudinal waves is similar as the reflection of transverse waves from fixed ends of this rigid support, as like this. The phase of reflected wave depends on whether the end of the pipe is open or closed, and how wide or narrow the pipe is in comparison to the wavelength of the longitudinal wave, like sound wave. तर इथे ह्या रिफ्लेक्ट झालेली जी लॉन्जिट्युडिनल वेव्ह आहे त्या लॉन्जिट्युडिनल वेव्हचा जो फेज आहे तो फेज कशावरती अवलंबून असणार आहे, तर ही वेव्ह कोणत्या एंड पासून रिफ्लेक्ट झालेली आहे, क्लोज्ड एंड की ओपन एंड, त्याच्यावरती अवलंबून असेल. आणि दुसरी गोष्ट म्हणजे ती जी ट्यूब आहे किंवा पाईप आहे ती पाईप किती वाईड किंवा किती नॅरो आहे त्या लॉन्जिट्युडिनल वेव्हच्या वेव्हलेंथ ची तुलना करता पाईप किती वाईड किंवा किती नॅरो आहे या गोष्टींच्या वरती रिफ्लेक्ट झालेला वेव्हचा फेज अवलंबून असतो. At the closed end, there is a least freedom for motion of air particles. Here, at this is a closed end, and at this closed end, there is a least freedom for motion of air particles. Thus, there must be a node at the closed end. There must be node at this closed end. The particles little beyond open end. The particles little beyond the open end are most free to vibrate. As a result, an antinode must be formed little beyond the open end. Here, what will happen? Here, air particles at this area are most free to vibrate, and therefore there will be antinode. So these are the boundary conditions. At closed end, there is node. At open end, near the open end, there will be antinode. The length small l of the pipe and the length capital L of ear column are shown separately in all figures. This is the length of the pipe This is the length of the ear column. The first mode of vibrations of ear column closed at one end is shown in this figure. This is the simplest mode. This is the simplest mode of vibration of ear column closed at one end, known as fundamental mode. Here, in this fundamental mode, ear column vibrates such that there is one antinode and one node. In this fundamental mode, there will be one antinode and there will be one node. Therefore, length of the ear column L is equal to lambda by 4. Here, we know that we have seen the properties of stationary waves here, and in that properties we have seen a property that distance between a node and successive antinode is equal to lambda by 4. Here, in this mode, ear column vibrates such that there is one node and one antinode. Therefore, this length of the ear column is equal to distance between node and antinode, that is lambda by 4. Here, lambda is the wavelength of the fundamental mode of vibrations in ear column, and if n is the fundamental frequency, we have phi is equal to n lambda. इथे लॅम्बडा म्हणजे इथे ज्या वेव्हज आहे त्या वेव्हची वेव्हलेंथ आणि n ही फ्रिक्वेन्सी ऑफ व्हायब्रेशन्स किंवा वेव्हची फ्रिक्वेन्सी. जर असे असेल तर वेव्हची व्हेलॉसिटी आपल्याला या सूत्राने लिहिता येईल, phi इज इक्वल टू n लॅम्बडा, अँड देअरफॉर दिस n इज इक्वल टू, therefore we can write n is equal to phi divided by lambda, and therefore n is equal to value of this lambda, that is equal to 4l. Therefore n is equal to phi divided by 4l, but this capital L is equal to small l plus e. This is the length of the ear column. Small l is the length of this closed tube or pipe closed at one end. This distance is the end correction. Distance between node and antinode. Distance between antinode and node is equal to this length of the ear column plus this end correction. So capital L is equal to small l plus e. This frequency is the minimum frequency of vibration of the ear column, lowest frequency of vibration of the ear column, and this frequency is called as the fundamental frequency, or it is also called as the first harmonic. This is the fundamental frequency, or it is also called as first harmonic. In the next mode of vibration of ear column vibrates such that there are two antinodes and two nodes. Yeah. If n1 is the frequency and lambda 1 is the wavelength of the wave in this mode of vibration in ear column, then we can write length of the ear column L is equal to 3 lambda 1 upon 4. तर इथे लेंथ ऑफ द इयर कॉलम म्हणजेच हा शेवटचा अँटीनोड आणि हा इकडे शेवटी असलेला नोड यांच्यामधील अंतर. आता प्रॉपर्टीनुसार आपण पाहिलेले आहे की नोड आणि त्याच्या लगतचा अँटीनोड यांच्यामधील अंतर लॅम्बडा बाय 4 असते. आता सेकंड मोड मध्ये जर आपण वेव्हलेंथ लॅम्बडा 1 अशी घेतलेली असेल, या वेव्हलेंथ लॅम्बडा 1, तर मग या ठिकाणी हा पहिला अँटीनोड आणि नोड यांच्यामधील हे जे अंतर आहे ते लॅम्बडा 1 अपॉन 4 एवढे होईल. त्यानंतर हा नोड आणि हा हा एंटीनोड, हे अंतर हे सुद्धा लॅम्बडा 1/4 इतके होईल. आणि मग पुन्हा हा एंटीनोड आणि हा शेवटचा नोड यांच्यामधील हे अंतर सुद्धा लॅम्बडा 1/4 असे होईल. त्यामुळे लॅम्बडा 1/4 प्लस लॅम्बडा 1/4 प्लस लॅम्बडा 1/4 इट इज इक्वल टू 3 लॅम्बडा 1/4. लॅम्बडा 1/4 ची बेरीज 3 वेळा केली तर किती येईल? लॅम्बडा 1/4 प्लस लॅम्बडा 1/4 प्लस लॅम्बडा 1/4 it is equal to 3 lambda 1/4. So this is the length of the air column, and therefore lambda 1 will be equal to 4L divided by 3. That is equal to 4L upon 3, and this length of the air column capital L is equal to small l plus e. That is the length of the pipe plus end correction. Therefore, lambda 1 is equal to 4 into bracket small l plus e divided by 3. The velocity in the second mode is given as phi is equal to n1 lambda 1. Therefore, n1 is equal to phi divided by lambda 1. Let's substitute value of lambda 1. Lambda 1 is equal to 4l by 3. Therefore, it becomes 3 upon 4L into phi. That is 3v upon 4L. If we substitute value of this capital L, we can write 3v upon 4L plus e. But here this phi upon, we have seen phi upon 4L plus e, it is the fundamental frequency or first harmonic. And therefore, we can write this n1 is equal to 3 into n. n1 is equal to n into 3n. This frequency is the third harmonic. It is first overtone. Remember that overtones are always numbered sequentially. In the next mode, air column vibrates such that there are 3 antinodes. 3 antinodes and 3 nodes. Air column will vibrate with 3 nodes and 3 antinodes in next mode. Here, if n2 is the frequency and lambda 2 is the wavelength of the wave in this mode, then length of the air column L is equal to 5 lambda 2 by 4. Here, in this mode, here this wavelength is lambda 2. Then distance between this distance, it is lambda 2 by 4. Then this distance again lambda 2 by 4. Again this distance lambda 2 by 4. This lambda 2 by 4, and this one lambda 2 by 4. So lambda 2 by 4 plus 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 lambda 2 by 4. It will be 5 lambda 2 by 4. So this is the length of the air column. And therefore lambda 2 will be equal to 4L divided by 5. Length of this capital L, value of this capital L will be small l plus e. So lambda 2 is equal to 4 into bracket small l plus e divided by 5. The velocity in this mode is given as phi is equal to n2 lambda 2. Therefore, n2 will be equal to phi divided by lambda 2. But value of lambda 2 is equal to, it is 4L divided by 5. This. And therefore, what will happen? N2 is equal to, we will get this, N2 is equal to 5 phi divided by 4L. If we substitute this capital L is equal to small l plus e, then N2 is equal to 5V upon 4 into bracket small l plus E. But this V upon 4L, V upon 4L into bracket L plus E, it is but nothing but N. And therefore N2 is equal to 5 into this N, 5N. This frequency is the fifth harmonic. It is the second overtone. Continuing in a similar way, for pth overtone, we get frequency Np as 2p plus 1 into N. We can find out frequency of any pth overtone by the formula Np is equal to 2p plus 1. So, what will be the frequency of seventh overtone? Frequency of seventh overtone will be, suppose N7, let's call it as, is equal to 2 into 7 plus 1 into N. It is equal to 7 into 2, that is equal to 14 plus 1 into N. It is equal to 15N. So in this way, we can find out frequency of any overtone by using this formula. Np is equal to 2p plus 1 into N. Thus, for a pipe closed at one end, only odd harmonics are present and even harmonics are absent. This ear column vibrates with these frequencies N, then 3N, 5N, 7N, 9N, 11N, then 13N, 15N, 17N, etc. This is the first overtone, this is second, this is third, fourth, fifth, sixth, seventh, eighth overtone. These are the different overtones. Then this first frequency is the first harmonic, this is the third harmonic, fifth harmonic, seventh harmonic, ninth harmonic, 11th harmonic. Thus, this ear column vibrates with only fundamental frequency and all of its odd integral multiples. That is, it vibrates with odd harmonics and it does not vibrate with even harmonics. So, this is about vibrations of ear column in a pipe closed at one end. Ear column in a pipe closed at one end vibrates with odd harmonics. Okay, thank you.